belts, check the sheaves to ensure they are in good condition. Check the grooves for rust and dirt, cleaning them with a stiff brush. Dirty sheaves substantially reduce belt life by abrading the belt. Then inspect for nicks or gouges because they can cut the belt. Wipe the grooves clean of oil and grease because they attack the belt materials. Use a sheave groove gauge and a flashlight to check the grooves for dishing or abnormal wear. Misaligned sheaves may wear more on one side than the other. If any clearance is visible, the sheave should be replaced. A new belt placed in the sheave should be flush with or above the outer diameter of the sheave. If the belt is below the outer diameter of the sheave, it is worn too much. However, this check alone does not ensure the sheave is not worn. If the sides are dished, the bottom corners of the belt may hold the belt out, but will wear quickly and work down in the groove. The best method is to use a sheave groove gauge, checking each groove, and then replace a worn sheave. When a sheave needs to be replaced, replace all sheaves in the drive, which increases the life of the belts. When using single belts and a worn sheave, they will seat individually and still have some pulling capacity. However, when a banded belt is used in a worn sheave, the belts all ride the same and cannot seat, which yields zero torque. In most industrial two-sheave applications, the motor is the movable component, while the driven unit is fixed in place. Rough align the motor in the center of its adjustments. This allows you to move it any direction after the sheave is mounted. Position the sheave on the shaft and rough align it using the string or straight edge. A taper bore sheave and bushing require extra care to be square to the shaft. The bolts should be just snugged up and the runout checked with a dial indicator to ensure that the sheave is square to the shaft. Place the dial indicator on the side wall of a groove and not on the face of the sheave. The face is usually not machined and may not be parallel with the groove walls. Tighten the bolts a little at a time so that one side does not pull in more than another, causing runout. Check the groove walls again to ensure the sheave is square with the shaft. Now the sheave can be checked for radial runout or eccentricity. This should be checked before the final positioning of the motor. If the sheave is eccentric, it is better to know that now than after the final positioning. Now the belts can be installed and the final alignment can be performed. When installing the belts, the movable component should be moved in so the belts can be placed on the sheave by hand and without prying them on. Prying the belts on breaks the wrap, the reinforcing fibers and reinforcing cords, severely reducing belt life. These belts should be discarded. Position the motor laterally so the sheaves are aligned, and if your machine has adjustment bolts for lateral movement, secure them as a guide. Verify that the alignment is good, rotating the shaft to ensure the sheaves are true. On multiple belt drives, adjust the belts so that they are all positioned with the slack side on the same side. As the tension is adjusted, the belts will not be able to slip, but will pull against each other and may damage the belts. The next step is to adjust the motor out until the proper tension is set. Be sure to turn the adjusting bolts the same amount so the motor moves straight back, keeping the sheaves in line. Too little tension allows the belts to slip and burn. Belt squeal is an indication of too little tension. Too much tension causes separation on the outside banding, leading to belt failure. The proper belt tension is the least tension that keeps the belts from slipping. This can vary for different belt types, belt speeds, sheave diameters, and drive configuration. And the tools to measure the tension can be very sophisticated, such as an ultrasonic sensor, or very simple, such as the rule of thumb. The long-standing rule of thumb has been to press on the belt with your thumb and measure the deflection, which should be about 1/64 of an inch for every inch of center to center distance. However, some thumbs are heavyweights and some are featherweights. An improvement on the rule of thumb is a small, inexpensive gauge produced by several belt manufacturers that measures the force applied and has a scale to check the deflection with a given force. Charts provide the recommended force for the various belt types and center-to-center distances. When installing new belts, set the tension 1/3 tighter and check it after the first few hours of running, adjusting it if necessary. Use a straight edge as a deflection guide, or in multi-belt drives, use another belt as the deflection guide. When the tension is properly set, make a quick check that the alignment is still true, install the belt guards, and start the machine. Be sure to perform all these steps, being as accurate and precise as possible to ensure a smooth running belt drive. The belt drive on this machine uses 3 belts that must drive sheaves on both sides of the belt. These are the double V belts. One belt is bad, having separated and lost a long section from one side. A sheave configuration like this puts tremendous stress on a belt because both the top and bottom side of the belt are subjected to compression and tension. For this reason, the reinforcing cord is in the center of the belt. These belts are size CC81. The CC refers to a double C size belt, which is measured on the inside. So this belt is 81 inches long on the inside, but is 87.4 inches on the outside. Only one belt is bad, but all 3 must be replaced. The other 2 are worn more than a new belt would be, and it is important to get a matched set, as variances in length affect the efficiency of the drive. Although belt manufacturers have much closer tolerances than they used to, there can still be some discrepancies from one run to the next. Some manufacturers mark the belts so you will know if you have matching belts. For example, the belts from this drive show the belt size, the manufacturer's name, and then the number 50. If a belt is 1/10 of an inch longer, it would be labeled 51 and so on. If it is 1/10 of an inch shorter, it would be labeled 49 and so on. Since all 3 of these belts have the same number, they are a matched set. Select a new matched set and remove the old belts. The tensioner is loosened enough to remove all the belts, and the new belts are placed on the sheaves without prying them into place. The tensioner is tightened and the belt tension is checked with a tension gauge. A few steps were left out of this belt replacement job due to time constraints. Some of these steps are: inspect and clean the sheaves, check the sheave for runout, both eccentricity and wobble, and check all the sheaves for alignment. However, if the drive runs smoothly and with minimum noise, the sheaves may be in satisfactory shape and may be in alignment. The critical steps were performed. All the belts were replaced with a matched set. They were installed without damaging the outside wrap, the internal fibers, or the reinforcing cord, because they were not pried onto the drive, and the proper tension was set. Hopefully, this set of belts will reach the design life of 25,000 hours. Belt drives are normally considered to be the real shakers in the industry, but they're very economical, are fairly easy to maintain, can carry heavy shock loads, have a high operating speed range, and a high service life. When time is invested on the front end to ensure a correct installation, the return on the dollar invested can be a hefty payback. Inspect the sheaves for wear using a groove gauge. Check them for proper alignment and runout, including eccentricity and wobble. Use the belt that fits the sheave and that will carry the design load. When replacing a worn belt in a multiple belt drive, replace all the belts using a matched set. Set the belt tension, making sure that it is tight enough so it does not slip. Determine the belt strand resonance and compare it with system resonance and other forcing functions to ensure it will not be excited by them. Replacing multiple belts with a banded belt will change the resonant frequency and may move it away from problem frequencies. Record this resonance frequency for future analysis. Calculate the belt frequency, realizing that multiples of it are most likely to appear in spectral data. Use enough resolution so that belt frequency harmonics will be separated from other energy, such as turning speed of one of the shafts. Check and correct belt problems before doing other work to minimize vibration, such as balancing. Belt-driven equipment can run smoothly, but like other power transmission sources, it requires a conscious effort to overcome compromises and keep the machine in optimum condition. Although many areas have been covered, providing a solid foundation for successfully correcting belt-related problems, and although we've demonstrated best practices for single and multiple belt applications, we realize each belt drive is unique and may require other steps and techniques to produce satisfactory results. Thank you for joining the thousands who have recognized CSI as leading industry with quality information, instruction, and application of PDM and RBM techniques. Whether you use sophisticated equipment and methods, or simple methods and equipment for minimizing belt-related problems, we are confident that the application of the tips and techniques presented here will dramatically improve your belt drive performance. We look forward to assisting you achieve success in your future endeavors.